In this video, we'll be looking at problem number 1 from section 24B. 24B in particular is looking at the application of derivatives. Interestingly enough though, for this video, we're going to be focusing on the first part of this question number 1. In particular, showing that the remaining area equals this equation. A equals 50 times quantity theta plus 3 sine theta. So let's go ahead and read the problem, and then we'll dive into that portion. A circular piece of tin plate of radius 10 centimeters has 3 segments removed, as illustrated. If theta is the measure of angle COB, show that the remaining area is given by A equals 50 times quantity theta plus 3 sine theta. We'll find that the second portion, with finding the theta to the nearest tenth of a degree when the area is a maximum, that's easy enough because they've actually given us the equation for area. So if we just take this as our function and then find our derivative, because we want a maximum, we set it equal to 0, we can go about finding that maximum theta pretty easily. Again, we're really going to focus on how we can break down this area, break down this region into pieces, and piece by piece find this given function for area. So to help us out, I've gone ahead and blown up this picture so we can get a better sense of what's going on. So we have here, this is B, this is C, this is our center, which means this is our theta. And we have our radii of 10 centimeters on either side. Now, to help us out, we really should try to divide up this area into familiar shapes. So right now, we can see this sector of a circle. Not so bad. But for this bottom section, we could do all sorts of things. We could try to do a right triangle, or maybe several triangles. The best method, or the easiest method to go with, would be to divide it up into triangles. Not necessarily worrying about right triangles or not, because with right triangles, to find their area, we're going to need to find this vertical length and this horizontal length. And if we don't have to, it'd be great to avoid it. So, with that in mind, we can divide up this section into 3 triangles. And we can figure out some additional information about these triangles to be able to find their areas pretty easily. So let's go with what we know and continue to label our picture. So we have an angle measure of theta here, that's COB. And because you have these 2 intersecting lines, these green portions are just continuing this radius to the opposite end of our circle. So we're creating a diameter. So let's say I label this point as D, and I'll label this point as E. So BD is a diameter, which means this portion from the center to D is also 10 centimeters, as well as from the center out to point E is also 10 centimeters. Now with 2 intersecting lines, I have vertical angles. We like vertical angles because that tells us that this angle measure, which would be DOE, is also theta. And for the remaining angles, so these vertical angles, which would be BOE and COD, we can find a relationship to theta so that we can describe them as well. At this portion, I'm going to pause for a moment. I want to make a quick note. We could describe our angles in terms of degrees, or we could describe them in terms of radians. Now, based on the way that the remaining area is described, we're going to focus on radians, because radians tend to play it a lot cleaner and a lot nicer than degrees. And you'll see why here in just a moment. So when we look at this supplementary angle to theta, we have a straight line, which means it's an angle measure of pi radians. You could also say 180 degrees, but we decided we're going to work with radians. So since this entire measure is pi, This angle then is going to be pi, that full straight angle measure, but we would subtract from it this theta because this is the remaining portion. So that means that angle BOE is pi minus theta, and COD is also pi minus theta. So now we have our picture well labeled up. Let's look at some of our formula for finding areas to see how well we can go about finding the area of this overall region. So in particular, we're interested in two area formulas. We want to look at the area of a sector, and then we also want to look at the general area of a triangle, not just right triangles, but any old triangle. So with area of a sector, when we describe it in terms of radians, we have 1/2 theta r squared. Now you're probably used to seeing theta over 360 pi r squared. That's true if you were dealing with degrees. But since we're in radians, this is the way that you would describe the area of a sector in radians. Then when we look at the area of a triangle, we should actually draw a triangle that'll help us to figure out what's what. So a general triangle, not necessarily a right triangle, we have, let's call this side B, we'll call this side A, and this bottom portion we'll call C. When we describe the area of a triangle, it's going to be 1/2 times 2 of our legs, so in this case we'll say A and B, and then we multiply it by sine of C. So this is the angle that's across from the third side. So as long as you have the angle between the two sides that you're using in your area formula, you're fine. You can find the area of the triangle really easily. Well, that works out well for us because look, we've got two sides, angle, two sides, angle, two sides, angle. And we don't say two sides angle for this top portion because again, that's going to be our sector. All right. So one last little piece that I want to make sure to list because we will find it super helpful. This is a trig identity. When you have sine of pi minus theta, which is also the same as sine of 180 minus theta if you're talking about degrees, it equals sine of good old theta. The sine values are exactly the same. That will be very, very helpful here, especially as we start to look at the area of these triangles where we have theta minus or pi minus theta as our angle measure. So let's get to work. Let's go ahead and set this up. So first let's look at the area of this top sector. So it's just that portion of the circle. So for that first area, we're going to use that area of a sector formula. So it means I have A equals 1/2 theta times my radius, which in this case is 10, squared. So that means I have 1/2 times theta times 10 times 10. So it's 100 divided by 2 gives me 50 theta. So that one's taken care of. Next, I've got this bottom triangle. We'll do this one next. So with this bottom triangle, I will use the area of a triangle formula, nice and general. And for that, I've got 1/2 first leg, second leg. Both of them are 10. That's very useful. So 10, 10. And then I multiply it by sine of this angle in between, which just happens to be theta. So that means I've got 1/2 times 10, which is 5, times 10. Hey, another 50, but this time with a sine theta. So 50 sine theta. Last but certainly not least, let's look at these triangles. You'll find that this triangle on the left matches this triangle on the right. They have the same measures for their sides, all 10s, but unlike this section number 2 that we just did, the angle measure is pi minus theta. So for both of them, both pi minus theta, so they both have the same area. So let's make it easy. We'll find the area once and then multiply it by 2. So that means when I'm considering the overall area of those two, so I have 2 of those, so 2, I am going to use that same formula for my triangle. So I have 1/2, my 2 sides, both 10, so 10 and 10. And then I have sine of my angle, which is pi minus theta. Pi minus theta. But then I remember I have 2 of them, so I'm going to multiply by 2. Well, goodness, this looks a lot like what happened in that second triangle, right? There's the 1/2 times 10 times 10, and we already knew that was 50. So now when I multiply it by 2, that gives me 100. And then I have sine of pi minus theta. Good news! This pi minus theta, in terms of sine of pi minus theta, not just the straight angle, the sine trig function equals to sine of theta. These two trig functions are equivalent. They are equal. So instead of saying 100 sine of pi minus theta, I can say 100 sine of theta, which means I now have all 3, or you could say 4, sections taken care of. There's my area of a sector, 50 theta, area of this bottom triangle, 50 sine theta, area of my 2 side triangles, 100 sine theta. So let's go ahead and add these up so then we have our overall area. So our total area, that's with adding up 1, 2, and 3, is equal to 50 theta plus 50 sine theta plus 100 sine theta. Oh, this is good. This is very good. Because notice what happens. We have the 50 theta, but then we have 50 sine theta, 100 sine theta. Those combine to become 150 sine theta. There we go. And if I look at both of these terms, I can factor out a 50, which leaves me with theta plus 3 sine theta. Oh, that is good. There it is. So that is our area. Now, I think the book may describe it a little bit differently. I think it goes about finding the length of various sides and using that to find areas and divide things up differently. You still get the same answer, different methods to the same destination. So with this, again, just in review, we found the area of our sector, which was this top portion, with an angle measure of theta. Then we found the area of our triangles, noticing that we had an angle measure that were vertical angles of pi minus theta, and then this vertical angle set of theta. Thankfully, all of our side lengths were 10, so that made it really easy when it came to setting up our triangle area formulas. And with a little help with our identity, that trig identity there of sine of pi minus theta equals sine of theta, we were able to make what could have been a really nasty problem into a not so nasty problem. So if you have any questions on how this was set up, feel free to post something in the comments area and I will try my best to get back to you as soon as possible. All right, hope this has been helpful.